My name is Bill Gady, and I have a presentation next door. So they pushed me up ahead in this room, unfortunately. And whoever I kicked back, I'm really sorry about it, but it can't be at two places at once. Anyways, I'm here to talk about the architecture of light. What does light itself look like? Now, the question people have is whether it makes any sense to ask what light looks like. We usually use light to see things. We want to see a table, a chair, we use light. How can we see light itself? Well, this is not a question of verification. It's a conceptual issue. Is light a physical object, or is light an abstract concept? An object is that which has shape. A concept does not have shape. What is the shape of love or of justice? So the question is, does light have shape or doesn't it? It's a black or white issue. It can't be both, or neither. Throughout the years, they have used several models for light. And one of them is the corpuscular model proposed by Isaac Newton. In the case of the photoelectric effect, carried out many years later, this model is what Einstein used to explain this experiment. He essentially said that we have corpuscles striking electrons, bumping surface against surface, and creating a current. So the model used by Einstein was the corpuscular or particle model. There's another model proposed previous century by Hertz and others such as Maxwell. They determined that light is what you see here, an electromagnetic wave. And you can see here in this model that you have the electric field and a magnetic field. We are replacing that today. We're offering a new model here, and that is the rope model. We're saying light is not a series of particles. We're saying that light is not an electromagnetic wave. We're saying that light is a rope that permanently connects two atoms in the universe. Every atom in the universe is connected to all other atoms through what we will call an electromagnetic rope. The word rope is used only as a way to describe this model because it essentially looks like what we would say in our day, in our macro world, what we would call a rope. Okay? As you can see, it's got similar features. However, a wave differs from a rope in that a wave comes out of the atom, goes off to nowhere. It goes in one direction. The rope extends between two atoms. The signal, which is a torsion, goes in two directions simultaneously. Okay? And this is again a physical model we're talking about here. We're saying that light has the shape of a rope, an electric thread and a magnetic thread, not a field. A field is a concept as opposed to a thread. Some of the features that this model can explain right offhand is we have in our current talk, our current language, we call this a wave length. Here we're going to call it a link length. Here we have amplitude, here you have amplitude. Here you can explain why the electric field runs at 90 degrees to the magnetic field. They oscillate around an imaginary axis. Why? Because any rope, and here I have a little model, extends one around the other. It has no choice but to extend around an axis, a straight axis. It's pulled tight. Okay? Another feature we can explain with this is the speed of light. If you do a very simple experiment at home, just take two clothespins, stick them to a rope. As soon as you touch one, the other one moves instantaneously. You cannot explain that with the current models where we have some kind of a string and we do the standing wave type of experiment. This has to be tied at the other end in order to do it. You cannot do it unless this is tied. You cannot do it like this if you want that to more or less travel straight. But you can do it with a rope. And again, we're not talking about a standing wave, we're talking about a torsion wave, moving along a rope. So it's a totally different mechanism for light. It explains the speed. It explains why light travels in both directions simultaneously. It explains why the electric field is at 90 degrees to the magnetic field and why one induces the other one into being, Faraday and Maxwell's laws. One of the features this model explains is frequency. If we increase the number of links, we will have more links per unit length, but the links will be smaller. If, on the other hand, we decrease the number of links, we will have longer links. And that is exactly what this equation is. This is Maxwell's derivation, C equals frequency times lambda, wavelength. So why is frequency inversely proportional to wavelength? We see it because that is the equation of a rope. Okay? Another feature that this model explains is an experiment that has baffled people for many years, and that's the slit experiment. The slit experiment consists of light turning corners, we can call it. Light tends to go around things, okay? But we don't need to curve light in order to do this. We can do it with straight lines. Here you have a pattern that is constructed completely with straight lines, and you can see a curve. And this similar mechanism is what light does with a rope. Here we have gravitational lensing and the slit experiment, both essentially the same experiment. We do it all with straight lines. We have a star behind the sun. The ropes are already connecting the atoms of this faraway star to the corona of the sun, which relays the signal to our eyes behind the moon. And here we have the slit experiment where we again go with straight lines. We simply have the atoms from the source connected to the partition, to the slit, and from there directly to the screen. Every atom is connected in this room. So the signal proceeds first from the source to the slits and then goes through the same channels, through these ropes, to the wall. In fact, what is interesting is that we can do the slit experiment without slits. And that's one of the things that people have not realized for a long time. We can get rid of the slits altogether and just put a needle. If you take a laser, which I have one here, if you take a laser, and you point it at a needle, you can create the slit experiment right there on the wall. You can do it at home, you'll find out that it's very easy. So the question is, how does a one-way mechanism such as particles or waves hit the edge of the needle and come inwards? We would think that it hits here and goes outwards. With a rope, you can explain it because every rope is connected to every atom on the screen. So the signal has no chance of getting lost. And another experiment we can explain with this is the famous EPR. Einstein, Podolsky, and Rosen in 1936 suggested a thought experiment saying that when an atom shoots photons simultaneously in two opposite directions, one can be visualized as going clockwise, the other one will be going counterclockwise. If we change the rotation on one, the other one changes instantaneously. And the question is, how can you achieve that with particles? The signal would have to travel faster than light from one source to the other. Here we can do it with a rope very simply, because the rope, in your end it turns clockwise, and in my end it turns counterclockwise. Vice versa. If you turn this one clockwise for your end, mine is turning counterclockwise. So no matter how far apart they are, if it's the same rope, they will turn in opposite directions. Now we can see that. Here I have a little simulation. You can see how it changes the rotation. For us, it's turning clockwise. Now we can turn it counterclockwise, and again, that depends on what position you're looking at light. So one place we can measure clockwise, the other one will measure counterclockwise. And finally, one of the things that the rope model can explain is another feature which is known as the grand unified theory. We try to unite light with gravity. So how do we do that? Well, if every atom in the universe is connected to all others, we can now for the first time conceptualize pull. We can see why, if two atoms are, well, not two atoms, but two objects are very far apart, the ropes tend to unite and pull as one. So it's a weak pull. Whereas as they come closer together, the ropes fan out. The closer they are together, the faster they are attracted to the other object. The faster the two objects come together. So the point of the thing is, of this presentation, is to show that light does have, or possibly have, a different configuration than what we've thought about in the past. It's not made of particles or waves. We're talking about a rope here. And we think that light does have some kind of physical shape. If it weren't so, we would not be able to stop light with our hands. If it were a concept. I cannot stop love with my hand. I cannot stop justice with my hand. The other things we talk about, the speed of light. What is it that's speeding? Hopefully it's not beauty or intelligence that's speeding. Hopefully it's a physical object that is speeding. So light does have to have some kind of shape. And we're proposing that it has to have shape.